We're now going to cover the last of Newton's three laws, and maybe the most amazing of all of them. Newton's third law is often called the law of action and reaction, and there's many ways to say it, but I don't like most of them because students misapply them. So the way that I require my students to know this law is as follows. If body A applies a force of some type upon body B, that means there needs to be two bodies, and those bodies need to be interacting in some way. So for instance, let's say there's a block, and that block maybe is setting on another block. Maybe this block. And they could be both setting on a third block. Or on a table, for instance, as I've drawn it. So this is A in our thing, and we're going to let this be block B. So body A applies a force of some type upon body B. One of the easiest ways to see this, and of course what we're going to want to do with it, is to draw a free body diagram. So I'm going to draw a free body diagram over here to the side of block B. And what we're saying is that the A is applying a force upon B. One of the forces that could be is that A is applying a normal force because it's touching B and it's pushing down. So it involves an object and a second object, always two. So the blue is A, it's the one applying the force, and the free body diagram we're talking about is the free body diagram of block B. And it's applying some type of force. My some type in this case was the normal force. If it does this, the third law says that there are some things that the other block has to do. It says then the red block, body B, must apply. It didn't say you could choose to if you wanted to. You must do this. You must apply the same type of force. It's got to be a normal force. You got to apply it to body A. Do I need a free body diagram, I guess, over here at body A? And now there's going to be an arrow that's going to be due to body B, and it's going to be a red arrow here, if you would. And it's got to be the same type. It has to be equal in magnitude. What does that mean? That means it has to have the same label. It has to have the same length. It's going to apply a normal force. Got to have an N. But it's going to point in the opposite direction. Now what's interesting about this is that if you consider these two together over here, you've got an arrow going up, in, and you got an arrow exactly the same length going down, in. And if you took your whole system to be this, that was the free body diagram you were drawing. So I'll draw that over here. Those two arrows would add together to be 0. So they cancel each other. And that's the reason that when you draw something like this, these internal forces inside here cancel out. Because both arrows are on the black diagram, and they're equal in size, but they point in opposite directions, so they sum to 0. But if you talk about the individual blocks, say the red block or the blue block, their free body diagrams only have one of the arrows on it. And so this can cause acceleration of the red block. This can cause acceleration of the blue block. But combined, There is no acceleration. Now, even if these things come apart, there is a point that we can treat it as if this was one unit, a very special place called the center mass. And we'll come back to that and talk later. So I've given you a lot of stuff to think about. Partly not just because I want to deal with third law, but I want you to think a lot about the third law and not just dismiss it because it doesn't look like you plug numbers into it like the second law. It is very profound. All of the conservation laws, conservation of linear momentum, conservation of angular momentum, conservation of energy, all these advanced things that we're going to cover in later chapters, actually, this is where they reside. They reside in the third law. The third law is an amazingly deep thing to think about. So, key things. Body A, and there's got to be a body B. So you got to identify the two bodies who are talking, interacting. Remember, forces don't just act on something. They have to involve an interaction of two bodies, like the Earth and Johnny. Johnny's weight doesn't belong to Johnny. It's a Johnny-Earth interaction. If the Earth applies weight upon Johnny, then Johnny must apply the same type of force, weight, gravity, upon the Earth that's equal in magnitude but opposite in direction. So if you had Johnny and you talk about his weight, there's that. But then you have the Earth, which of course I'm not going to draw to scale. I have big enough paper, obviously. Then there is a force on the Earth provided by Johnny due to his gravity that'll be exactly equal in magnitude and opposite in direction. Think about this. You drop a ball and the Earth accelerates the ball down. But did you think about the fact that the ball accelerates the Earth up? It's true. Now, the Earth is very massive, and so for a given force, the acceleration is very small, whereas for Johnny, having much less mass and the same force, he has a much bigger acceleration. But there is a combination of force pairs between them. What is not the same in the third law force is to say that Johnny's weight is equal and opposite to the normal force. They're not the same type of forces. One's normal, one's weight. They can't be the forces talked about here. Now in Giancoli, he does a pretty good job about the nature of the two bodies and about the equal in magnitude and opposite direction, but he does leave out this idea that it has to be the same type of force. Does this third law always hold? Well, in more advanced things, when we start talking about forces that are not contacting, like gravity and such, you have to ask that there's strong and weak forms of this law. For instance, not only do these forces be equal and opposite, but we're only concerned particles. With larger things, say a bridge, they actually have to line up right on top of each other. Otherwise, the bridge would just start spinning faster and faster on its own. So there's even more to this law than what I've given you. Learn and memorize the three laws and how the three laws should be written both in words and in, if you want to, in equations. Usually in equations it's written like this. The force on A by B is negative of the force on B by A. So if you reverse this, it's on by. And the minus sign means changes direction, but otherwise it's exactly the same in magnitude. Alright, this covers all of Newton's laws. You only really get good at Newton's laws by practicing Newton's laws. There are many videos with many examples in lots of different things where things are interacting, touching, moving. By the way, for instance, interacting, if this thing was sliding, there might be friction. So if this thing was sliding this way on the top, there might be a friction force on that blue box that attempted to stop it. And who would apply that friction force? The bottom block. Then the bottom block would have a friction force in the opposite direction applied by the blue block. Equal in magnitude, opposite in direction. That's the concept of the third law. All right, we'll see you in other videos.